Good morning, sir.
Yeah, so I was just like, so shall we, start, sir?
Yeah, please.
Okay, yeah, thank you very much. Is my presentation visible, Appa?
Yes, sir, it is visible.
Thank you. So, yes, Appa?
Just make it in presentation mode.
Yeah, I have put it in presentation mode. If it is not in presentation mode?
Not, sir.
Why I am not able to? Just a minute. I am doing share screen. Just a minute. Share.
Sir, your screen is visible. Presentation is also visible, but just in a grid view.
Yeah, can you come this side? Okay. It is okay. Share. I am sharing my screen. I thought, and now I put F5. Okay. Hello.
Sir?
It is still in that presentation mode?
No, sorry. I can see your last slide. Actual lamp lightning.
Can you come down this side?
Yes.
Yeah. So very good man. Like till I would just keep on talking till all this. I have just to make it short. I have made one presentation of for the things to be covered in a short time. But anyway, it's fine. So I would continue with my So chief guest of the function.
Hello. Sir, you can continue as it is. Current screen is visible.
Okay. That is fine. Yeah. Thank you. So, chief guest of the function, Dr. Guru Prasad Rao, our Honorable Director, College of Engineering, Pune, Professor Ahuja, my co-convener of this program, Appa Sahib, the invited speakers, faculty, colleagues, participants, a very good morning to you all. We are here for the ATAL AICT ATAL FDP on future scale technologies in 3D printing and design that would be conducted between 29th November to 3rd of December. And this is what the organized by Department of Metallurgy and Material Science. Like it's our tradition that we normally begin any of our function with traditional lighting, virtual lighting of the lamp. So that's what I would invite Dr. Ahuja and Dr. Guru Prasad to do the traditional lighting this lamp.
Sir, your voice is not audible.
Yeah, so I will continue. Like I would be talking about three aspects in my short talk. So this is what I would be first talking about department as such, some introduction I would be giving, and apart from that, I need to this August gathering I will introduce our director as well as our chief guest. So this is what the department, if I really look at, we got established in 1948 under able leadership of Professor G.K. Ogle. There in that time we started the UG program. Then we started 1959 and 1987. We started two respective PhD programs. One was in physical metallurgy, and another one was in process metallurgy. Then gradually our journey continued. So I'm not reading all, but now, like as such, recent, if you really look at the developments, that 2014, our UG program, it got accredited, and that accreditation still is okay, continued. 2015, our both PG programs, physical and process metallurgy, they also got accredited. Now 2019, our physical metallurgy program, it was changed, its name was changed to materials engineering, and that whatever the accreditation, it got continued. And 2020, like our degree, okay, that is what it is approved as metallurgy and materials technology. So that is what the degree we would be offering to our students. Now, looking at our vision mission statement, quickly, I would say that our department strives to achieve excellence in quality of metallurgy and material science education imparted and become the leading department in the nation in frontier areas of relevant technology. That is what the vision we are carrying, and it would be okay. Obtained through various mission statements like foster creativity, innovation, productivity, social responsibility awareness, then highest quality knowledge base, providing the students capable of offering technical support to industry and accept challenges and inculcate capabilities in students to function as educators, scientists, researchers. Okay, that is what we wish to make the students capable of all these things. So as such, our quickly I would glance at the academic program. It is what we have got BTech intake of 60 plus 6, okay, lateral entries, and 9 through okay, foreign nationals, NRI, and also that goes to 75. And each of these PhD with this PG program, we got entry of okay 18 each. So our intake becomes 111. And so we have got, apart from this intake, we have got over and above this PhD, there are okay ongoing 24 and completed 7. So we have got various government sponsored projects from DST, BRNS, UGC, AICT, ISRO, all this. And apart from that, many industries, they also contribute okay in day-to-day functioning and various activities of the department. So that those include John Deere, IMP, Specialty Center, Eaton, Cummins, Jain, Endurance, KPIT, and other professional bodies like Alucast and all. So if we really look at the major facilities, if you wish, we have, okay, scanning electron microscope, XRD, dilatometer, differential thermal analyzer, differential scanning calorimeter, high temperature wear test, cryogenic bath, micro hardness tester, planetary ball mill, okay, nitriding gas carburizing furnaces, high temperature UTM, plastic injection molding, polymer extruder, potentiostat, galvanostat, laser material processing facility, BET, powder atomizer. So all these major facilities we have, we can do plenty of okay research, plenty of work in our area. Now it's my pleasant duty to introduce the chief guest of our today's function, Dr. Guru Prasad Rao. He is the director and mentor of leadership team at Imaginarium India Private Limited, Mumbai, one of the largest okay 3D manufacturing company. So like if you, he is a okay, technocrat, okay, and IIT Bombay PhD recipient, technocrat with over 30 years of experience in encompassing industry and academia. He has okay performed various industrial assignments with okay all well-known industries like Titan, Tanish, Crompton Greaves, and currently okay looking after his assignment at Imaginarium. Okay, then he is okay technocrat, so academic and okay both industry front. So design, his background of design, okay, that comes from his ISc degree in okay design, and he teaches okay taught this thing IISc, NIFT, JSSATE and NTTF. Then he was ex-professor and head project office IICD Jaipur, teaches courses on emerging technology and its impact at SPJIMR and KJ Somaiya Business School, mentor at KIIT, TBI Bhubaneswar, associated with many industries bodies, CII, FICCI, NASCOM, BIS, IAMF, ATAL Innovation Mission. Presently, he is a part of member CII National Committee on Design, and currently his focus is on DFM for metal 3D printing, medical application, skill development, besides technology mentoring and partnership across many domains. So that is what he is, okay, a well-known, okay, authority in 3D printing. My next present duty is introducing our director. He is our source of inspiration, officiating director at COEP. He has got, okay, to his credit over.
Professor Bhutti, you can
Sir,
skip that. Please
oh, sir,
skip that.
please, one or
Please,
two
please,
words.
please. No.
Just
Please.
quickly, that is fine.
No. You can skip.
Yeah, okay, that is fine. So nice. Thank you very much, sir. Yeah. So he is there, always helping us, and then
అది
we are,
వైట్
okay,
పాస్తా రా
under his
వైట్
able
పాస్తా చేయడం
leadership, we are
వైట్ సాస్
continuing
చేయడం మైదా
all these
మిల్క్ వేస్ట్
activities.
చేస్తారు
So this is what I wanted to
Which is-
ask from my end. Now I invite Professor Ahuja. Okay.
బ్లాక్ పెప్పర్ వైట్
All
సో
the
మైదా
participants on
మైదా
behalf
మిల్క్
of our
వేయాలా
institute. Thank you very much.
అది రాలే ఈరోజు ట్రై చేస్తే ఇంక మా ఆయన చెప్తా ఉంటే ఆల్రెడీ పన్నాడు కదా మళ్ళీ ఇంకా
Some
సరిగా
audience, okay, their voice, okay, they are requested to mute themselves.
చేయాలి ఆర్గాన్ జ్యూస్ అవన్నీ తెప్పించాము అదే ఆర్గాన్ జ్యూస్ దొరుకుతాయిలే
Ahuja sir, am I?
Yeah.
Please,
No,
yes.
there was some disturbance. I was waiting for
Thank you.
everyone to be muted. Yeah.
Okay.
Thank you.
Good morning, everyone. Our chief guest, Dr. Guru Prasad Rao, who's the director and mentor at Imaginarium Private Limited, an enthusiast who has given himself to the cause of furthering education, more so in the domain of 3D printing and doing phenomenal work for the country. It's an emerging area, and he has contributed in this domain of additive manufacturing and also undertaken research to grow this technology. So thank you, Dr. Guru Prasad Rao, for being with us this morning.
My pleasure.
And always finding time for COEP and helping us in many ways. And today, on behalf of COEP, the faculty and staff and students, we welcome you for this inaugural function on 3D printing and design. Professor Sandeep Bhutti, head of the Department of Metallurgy and Material Science, Mr. Appasai Pacharne, my other faculty colleagues from the Department of Metallurgy and Material Science, and dear participants. Once again, a warm welcome to this FDP on 3D printing and design, which is being organized by the Department of Metallurgy and Material Science at College of Engineering, Pune. We are indeed Privileged to have you with us, be a part of this FDP. And I'm sure the learnings and the interactions that will happen over the week will give each one of us new insights into the theory and practice of 3D printing and design. I'm told that there are experienced experts, teachers coming from diversified backgrounds to speak to us on different themes during the conduct of this course, which is spread over the entire week. Short-term programs as these help us rejuvenate and deep dive into new emerging areas. And when we talk of Industry 4.0, 3D printing cannot be left behind. And while we talk of 3D printing, people are at 4D printing. Of course, the fourth dimension relates to metamorphical change of the material, material taking shape over a period of time, which means we use programmable materials, material which is 3D printed, gets its fourth dimension over a period of time. But it's an exciting domain. And we are very happy that we have so many faculty enthusiasts from all over the country to participate in this 1 week FDP. I verily believe, and on many occasions, time and again, I have said this, that the future lies with materials. Anything that we want to produce, any concept, any idea that we have, by and large, gets culminated into a service or a product. And if it's a product, we have to think of ways of creating the product, of manufacturing the product, be it electronic product, be it a product based on concepts of electrical engineering or mechanical engineering, whatever be the nature of product, it needs to be manufactured. And prior to 3D printing, which emerged in the 1980s as an alternative, a new technique to manufacturing. How was manufacturing conceived earlier? We were using a primary process to create the raw material, which is generic to be used by people for wide variety of applications. Steel, for instance, in different forms and shapes was made available. And then we applied secondary processes, be it metal cutting, to shape and size that raw material, that steel in some form, let's say rolled steel, to have required shape and dimension to serve a particular purpose. Or if there was no metal cutting, then we were trying to shape the metal through maybe, let's say, a drawing process, or through a process of extrusion, or through a process of forging, and trying to give shape to the material with the required, to get the required size also for a given specific function. And here is a technique wherein we just use the basic raw material, maybe in the form of pellets, powders, liquid resins, to give us the end product, which could be complex in nature. There is a lot of research going on to find out or to establish accuracy of the products and the finish or the quality of products that we get through 3D printing, and the speed at which we can get products through 3D printing. But it's a new emerging area. And ultimately, what are we doing? We are playing with materials so that we can get the required strength. We want the product to be lighter, to be cheaper, to be stronger. And then ultimately we play with different composition of materials. And 3D printing gives us this advantage of combining materials so very easily. And it's a very interesting domain. It doesn't end with the physics of the material, but it also requires one to know the biology, because now we are also bioprinting. We need to know the chemistry of the material. We need to understand the mathematics that goes behind the synthesization of material, and so on. So it's a wonderful world of materials to form products, components, used in a combination of ways. And 3D printing is one of those techniques which facilitates this. I'm sure in this course, you will learn many new things. And when this online form of learning is away from us, on behalf of the Institute, I invite you to see our labs, the best of facilities that we have created in the Department of Metallurgy and Material Science, and in particular the 3D printing lab, which has all kinds of printers and plotters. Printers, 3D printers, which are made in the lab itself. A lot of work is going on, a lot of research is going on. And I invite each one of you to come and experience these labs, be hands-on on these machines, and experience the joy of creating your own products with the design that you have conceived. A wonderful technique which also requires hands-on exposure. We will try to facilitate as much as it is possible in the virtual mode, including giving you glimpses of the labs. But do find time to visit us and give us an opportunity to showcase the labs to you. With these few words, I once again welcome you all to this FTP in the ATAL series of FTPs, which is approved by AICTE. And I also thank the AICTE officials for giving us this opportunity to run this FTP on 3D printing and design. Once again, a very warm welcome, and wish each participant a meaningful, joyful engagement with speakers during the entire week. I would also like to thank once again our chief guest for finding time to inspire us and guide us with his experience and his motivating words. Thank you, Dr. Guru Prasad Rao, for being there for us this morning. And thank you, Professor Butti and your team for coordinating and coming up with this FDP. A lot of efforts are required to organize an FDP, get connected with people, request them for their time slots, identify the appropriate topics, and connecting those topics to ensure that the learning is continuous and smooth. So thank you, Professor Butti and team at the Department of Metallurgy for organizing this FDP. Thank you. Thank you all. Over to you.
Yeah. Thank you very much, Professor Ahuja. So under your leadership only, we are able to do all those things. So that is all there. Now I would request our chief guest, to please address the Dr. Guru Prasad Rao to please address the August gathering. Thank you. Please, Dr. Guru Prasad.
Thank you, Professor Sandeep Bhute, for this wonderful opportunity. I'd like to thank Professor B.B. Ahuja for his kind words and, setting the context for this FDP. And I think whenever we think of Maharashtra as a technology space for learning, immediately three things occur to our mind. One is IIT Bombay, COEP Pune, and NIT Nagpur, and in a way, in the region, Pune being in the middle, has the best of both the worlds, with industry right there, and you're able to actually translate ideas into reality. And I think what I learned from Professor Bhute, the lab facility seems to be the best in the world. They have everything that is required for additive manufacturing, to do the research, design, and offer services, because they are sitting right there, just like Silicon Valley. They are in the automobile valley of India, where a lot of industries are around, the Tata Motors and various auxiliaries, and even you have an auto cluster there in Pune. That way, I think even the students, what they're learning, and today, for having consolidated this, COIP has been also taking this leadership, to train faculty across Maharashtra. And I've been witnessing, whenever COIP calls me, because it is with respect, and it is like a temple of learning. When you get call, it is worshipful, and really, I'm very happy to see there is a top-down approach of leadership driving the whole thing. And Professor B.B. Ahuja, with his passion and as a subject expert himself, driving it. I can see now that there is a very nice connection. And what can happen to FDP, when such a beautiful, things are falling in place in order to deliver, such a wonderful program. I'm sure the faculties will take advantage of this. And it is like lighting the lamp. You're lighting the lamps of the faculty in FDP. They again go and enlighten the students. And at the end, industry is the beneficiary, the skill development. And today's FDP, they've also given 3D printing and design. Actually, it should have been other way around, design and 3D printing. If you don't mind it, it doesn't matter. You have to mind it first before it can materialize. And so design is where everything starts, actually. In the value chain of what we are building, it is design. From there, of course, what to do, what to design is very, very important. And then comes the 3D content creation. Then comes the translation to machine readable formats. Today we have new formats coming. STL was 35, 34 years old, and it is still there, but we have 3MF, AMF, VRML, and XML, and so many other new formats coming because they're better, they're lighter, and that's what makes humankind to go beyond solar system, to boldly to boldly go where no man has gone before, kind of thing. They're thinking of 3D printing a colony on Mars with Martian soil, you know, and it is not just a joke or a fantasy, but people are actually working on it, trying to validate, is it possible? Then the entire design can be transferred to Mars or Moon or whatever, maybe an asteroid, where they can actually set up, because the the spikes will go at speed of light, and portability is very high. That means you are able to push more, information than what currently the file formats offer us today. I think Professor also mentioned about the Industry 4.0, where 3D printing is a very important actor. The cyber physical systems, the so-called the physical side is offered by the 3D printing. In fact, I emphasize on the trinity of manufacturing. It is the CNC and the 3D printers and the robots. They coming together to make the future of the world. It will not be man-made anymore. Man created, but it's all made by these three. That will be the future. Wish you all the best. Great success to this program. I'm sure we'll have one more occasion to meet, a couple of occasions to meet. We're going to have a virtual tour of Imaginarium. And I come from industry background, so my vocabulary, my approach would be different. Pardon me, faculties. I always say what we can teach faculty. It is to kind of trigger your thoughts. When you go back and try to teach, you get a lot of confidence now. Looking at the 4-5 days of program, what you have, that gives you enough of what I can say masala to create your own. Go ahead and make your own presentations, which will make more appealing presentations. And wish you all the best. Thank you, Professor Bhute, for this wonderful opportunity, and also Professor Appaswamy Sab for giving links and making it possible to reach you all. And I would like to again meet you all. Have a great day. Gave of learning, and I would also be learning from your questions, and I think that is very important. Be like a student, ask questions. That is very, very important, because that's what makes faculty also alert and work harder. And when you go back to students also, students need challenges. So the quiz part of it, the learning be fun. And I'm sure you're going to have great fun in these coming days, and learn and go with more value back to your class. Wish you all the best. Thank you. Thank you so much.
Thank you so
Yeah,
much.
thank you, Dr. Rao. It was a wonderful inspiration, a kind of talk you have given. Yeah, over to you, Appa, for conveying vote of thanks.
Okay. On the behalf of College of Engineering, Pune and Department of Metallurgy and Material Science, I am very thankful to Dr. Guru Prasad Rao for this occasion, inauguration occasion of the 3D printing and design for FDP. And I am very thankful our director sir for his continuous support, encouragement, and guidance throughout the last 4 to 5 months to make this ATAL online FDP for successful or this point. Again, I am also thankful for Dr. SP Bhuti for his guidance to make this FDP successful. And also very thankful for all the official for AICT and ATAL to giving the opportunity to organize the FDP on the 3D printing and design, and not least last, all the participant who are participated in this FDP to make a grand success for this program. Thank you all of you once again.
Yeah, thank you. Now, maybe I like what is important that to set the ball rolling. Okay, it is none other than our beloved director, Professor Ahuja, BP Ahuja. He would be okay initiating this process. So maybe, sir, you want to immediately start, or you want some 1 or 2 minutes break?
No, we can start immediately. I just need 1 or 2 minutes to set
Yeah,
up
yeah,
my
that is fine.
presentation.
Yes, sir. Yes, sir. Yeah.
Yeah.
Appa, I hope you are done, sir, host, co-host, and all.
Yes, sir. Sir has already made a co-host.
Okay.
Okay.
I would just like
Yeah.
some error is appearing. Is it
Is
okay?
my screen visible, or
No, sir. Your video is visible, sir.
you have given me those sharing rights?
Yes, sir. You have already made a co-host. Sir,
Yeah,
your
yeah.
screen is visible.
Now, yeah, now it is there. It is there. Yeah, and like
Yeah.
yeah, screen is visible, sir. Now.
Yeah. Just give me a minute.
Yes, yes, sir.
Yeah. Can I begin?
Yes,
Yes,
sir.
sir.
Please.
Yeah. Uh, Good morning once again to all the participants, faculty, colleagues who have joined on this AICT's ATAL online FDP on 3D printing and design. We will just deep dive you into the technology, introducing some of the basics and the work that is being done in the laboratory at College of Engineering, Pune. So if you look at manufacturing approaches, we have the move approach, where we form metal either when it is hot or cold. The remove approach, where we talk of metal cutting, and then we have additive manufacturing. So there are two areas of concerns when we talk of manufacturing. whether we are moving material or removing material or whether it is adding material. We have to make sure that whatever is being made has a flexible strategy wherein we make use of the machine and the material controlled by digital data, and which evolves around the design that has been created by us. So flexibility is one such concerning parameter. And whatever we produce, we want to ensure that it is with greater reliability, having larger product life cycle, which means that anything and everything that we produce must have quality to ensure the desired reliability, sustenance over a given period of time. And to achieve this desired quality of product, it means that we have to work closely on the variations in dimensions of the parts, the tolerances that we provide. Stricter the tolerance limits, greater or higher would be the manufacturing cost. So whether we are moving material or removing material or adding material, these concerns always remain. And we are in times when we are moving from macro manufacturing into the nano regime, where products are getting smaller and smaller by the day, smaller in size, smaller in dimension. So products are getting smaller, reliability is increasing, and we expect increased performance from these products, which means ultimately that we have to have improved decision making. We have to provide for adequate tolerancing as we go down narrower regime. We have to use appropriate tools to get us parts and products of required shape and size as we move from macro to meso to micro to nano regime. Concern is also about how do we hold those parts, small components, when they are to be machined. How do we inspect those parts? So how do we provide for fixturing, holding those parts, tooling? How do we go about manufacturing? And then how do we go about visualizing the part or the component that is made? Is it acceptable or one has to reject it? So we need to look at the suitable metrology for dimension checking, for evaluating the surface roughness of the part, to evaluate the functionality of the sub-assembly and the product as a whole, and then to carry out predictive modeling, which can help us establish the reliability of the product over a period of time. Now, these are some initial concerns that one has to keep in mind while designing any product. And this design, which ends in the product, in the form of a product, could be using the move technique or the remove technique or the additive technique. But these have to be kept in mind. And more so, we have to understand that whatever we create, which is digital today, driven by digital data today, must have a flexible approach and must carry the required quality to establish reliability and greater product life cycle of the device that we are trying to develop. A quick look at the industrial revolutions and how 3D printing is impacting Industry 4.0. And this has happened over a period of time. Most of us would be aware of what Industry 4.0 is right now. And while we are speaking of Industry 4.0, there is already a 5.0 called Society 5.0. And people are working in the 5.0 domain while we still talk of Industry 4.0. And if you see the progress over the years, we realize that it has taken quite some time to move from the first to the second industrial revolution. And then from the second to the third, still took a couple of decades. And from the third to the fourth, even lesser decades. So what this slide is trying to tell us is that as we are going to become more and more digital, as newer and newer technologies are going to emerge, this would happen in a shorter period of time. What does this mean? This means that we as teachers have to keep abreast of the emerging technologies to bring the latest to our students. We still cannot be teaching our students by the book. Today, information is available to the students at the click of a button. So why should they listen to us? Why should they come to us? They will only come to us if we provide them with the current developments, the current happenings. And the time taken to come up with a newer technology is so short-lived. They say that the half-life of technology is 2 years, which means at the end of 4 years, by the time a student passes out, half of the knowledge, what he has acquired or gained at the institute, becomes obsolete. The rate of obsolescence is so very high. And in such times, we are talking of emerging technologies, using emerging technologies, adapting to the needs of the emerging technologies. So the time span is becoming shorter and shorter with more and more digitalization happening. We becoming more and more data conscious because data is now easily available, which has been extracted from the past. In the past, we were not storing data. Now we are storing data, processing that data, analyzing that data, and then predicting what could be the future outcome of a given situation. So this Industry 4.0 tells us that yes, these are the emerging technologies, 3D printing being one of them. And though this emerged in 1980s, in the recent years, its acceptance has been accelerated to a large extent. These are some of the core technologies which work around Industry 4.0. Dr. Guru Prasad Rao talked of using robots, simulation, CNC machines, big data analytics, augmented virtual reality. Augmented virtual reality in time to come may replace teachers in the classroom, because a student will get a feel of the real world through the virtual platform. He will get insights into the product, its sub-assemblies, its components, as though he was actually seeing them in real time. Education will change to a great extent with augmented and virtual reality coming in practice. And then, of course, 3D printing, which today serves as printing or manufacturing on demand. We are yet to use the 3D printer to its fullest extent of mass production, unless we have a large number of printers which are cheaper in cost, and then we use each of these to print number of products at the same time for the same component at the same time. So if you need 100 pieces, we may have 100 printers installed, very cost effective, and every printer producing one component. And we are able to make 100 components in whatever time frame for producing one component. In that same time frame, we produce 100 because we have 100 printers on the line. But we are working on the speed of the printers. I'm sure all of us have heard of this company called Tesla. Tesla, which came into existence in 2003. It's barely 17, 18 years old company, heavily relying on additive manufacturing or 3D printing. 3D printing most of its parts which go into the electric vehicle. They extensively use robots for assembling their cars, their electric cars. And a lot of simulation is done to avoid field testing of cars, whether it is the performance of the car or whether it is the crash test of the car. Everything is done in the simulation mode. And they have been able to reduce their manufacturing and testing time, assembly time. And they are able to compete with the others. And not only compete with the others with a newer technology in place. And they have been able to revolutionize the use of autonomous and electric cars in a very short span of time. Why? Because they're using these technologies. One of them predominantly being 3D printing or additive manufacturing. So earlier people were thinking, or people were having their factories away in specified zones, and then sub-assemblies were transported to one unit, one factory from different offshore factories, and then the product was assembled or is assembled and sold. Today, the factory is established very close to the market. The service center is also established closer to the market because it is one machine which is capable of producing variety of components. Variety of components with all kinds of complexities in shape and size. And then one can use robots to assemble these components into a sub-assembly and sub-assembly into a finished product. The kind of competence The skilled labor that is required is also changing. It's changing very, very rapidly. I'm not sure if you know this, that 70% of the programmers in the world are self-taught. We are now wanting our students to become lifelong learners, self-learners, self-directed. Self-direction comes from curiosity. And curiosity will help us to imagine and create newer products, newer devices, efficient devices. So I need to be self-motivated to be able to think independently and to be able to solve the problem using skills such as critical thinking, coming out not with one but a couple of solutions and trying to make use of the best solution, which according to me is the optimistic solution or the optimal solution. So 3D printing is viewed as a disruptive technology, something similar to what was conceived by Steve Jobs and Steve Wozniak in the 1970s when they first created their Apple machine. And today, it is these larger companies which will drive the future of technology, Apple being one of them. When we look at 3D printing, there are certain challenges. Challenges on the surface finish, challenges on the production speed, challenges on the cost of procuring a machine, challenges of getting materials in, let's say, liquid form, powder form, whatever be the nature. And then we have to make sure that we create alloys using a combination of materials to give us the desired strength, the desired functionality of that component. We are trying to achieve consistency in product manufacturing and trying to ensure that there is not much variation in dimensions between the first component and the second component and the third component that is made on the 3D printer. Strength of parts. So once we have an idea, we have conceived a thought, an idea, converted that idea through a process of design into a product, we need to quickly make the product. Right? And that is where additive manufacturing comes in. So rapid prototyping has rapidly moved from the industry to the university to personal accessibility. Imagine you have a small machine at home and you put cheese cubes into the machine and you add some flavors or essence to the cheese cube and then print or lay cheese onto the biscuit, which carries the essence, the flavor that you want. And you can have your biscuit and the cheese too. So it has rapidly moved from the manufacturing domain into the personalized domain. And universities, colleges have a role to play in providing research in developing this technology further to meet individual needs. So they say that if you can slice an object and if you can glue or stick the slices back together, then you can call it as 3D printing technique. Though it is a slow technique, but it is getting faster by the day, with more and more research coming in to make these machines faster and faster without compromising on the surface finish and the accuracy of the component or the part that is being made. And if that can happen, I think everybody will move on to 3D printing, especially for those machines, heavy duty machines, which were manufactured 20, 30, 40 years ago, have now lost some of the parts. They are broken, they are chipped. The parts are not available in the market. One can certainly reverse engineer and make parts to repair, let's say, a turbine blade, or such heavy duty machinery, which is no longer manufactured and one has to replace some parts. Maybe then we can make use of 3D printing as a technique. So printing as such was coined and emerged in the 15th century, but it was not 3D printing. It was printing on paper, printing on cloth. Today we talk of wearables that can detect body parameters. But in those days, these were simple techniques of printing from 2D to 3D, and now we talk of 4D printing. And what the concept was that we would want to reproduce the images, reproduce the text, the data, the picture. And then over a period of time, we have been using a couple of techniques to create this. So additive manufacturing is a new class, a new technique. Used for building physical models, for creating prototypes. So unlike CNC machines, which is also driven by digital data, additive manufacturing, instead of removing materials, it adds materials. It adds liquid, it adds powders to form complex parts, layer by layer. Could be paper, could be plastic, could be metal. A wide variety of applications can be achieved when we put 3D printing into practice. Now, if you look at the subtractive technique, you have a primary process to create the material. We gave example of a rolled steel. And then using subtractive techniques, whether it is tubes, whether it is pipes, whether it's a solid rolled steel, whether it's a sheet metal, we use subtractive techniques To create the object, we remove material so that we can achieve the required shape and size. And whatever is removed is scrap, is waste. But primarily we use one manufacturing process to create that sheet metal, to create rolled steel. In additive manufacturing, to a large extent, of course, we do use, let's say, fused deposition modeling technique, FDM technique. For example, we use wires which are extruded from the pellets, and that wire is fed to the nozzle, which is heated. Let us say we use 3 ABS plastic, heated to 200, 220 degrees Celsius. And that plastic in its molten form is deposited layer by layer. But by and large, 3D printing, we can also use the material in its existent shape, or maybe we have to draw out fine powders and then put them through one of the 3D printing techniques. There are different methods of 3D printing. We get the required object. So apart from the build material or the support material that is required for building the object, that support material is the waste that is created, but the wastage that is created is very, very minimal. And today the advantage is that you can use directly the pellets, the powders, combination of powders, and using different processing techniques. Like in metal cutting, you have a turning machine, you have a milling machine, you have a drilling machine, you have a shaping machine, we have a grinding machine. Here also different machines, different methods are used depending upon whether we are using liquids or whether you're using paper or whether we are using plastics, different machines. We have bio printers or bio plotters using a different technique to plot bony structures, to print bony structures, and so on. So here we see that with additive manufacturing, there is less wastage, and a complex part can easily be achieved. Not only that, once we get the part which is made from subtractive technique, it may go through a tertiary production process. Let's say it will have to be, the object has to be case hardened in case of gears, or it requires some special heat treatment. That may or may not be required if one is going through an additive manufacturing technique, because we can use a blend of powders to create materials of required strength, having the required properties. And we can ensure proper characterization of the material properties when they are mixed in certain percentage to give us the required component of shape and size and finish. So why is 3D printing considered so exciting? Because we can create 3D complex shapes. It's lightweight in construction. There are many times, in order to save on cost of manufacturing, even if you want to make a component lightweight, we are not able to do so because manufacturing cost gets added onto it. Here, while producing the component itself through additive manufacturing, we can create a lightweight structure with pores and still ensure the adequate strength the material will possess. Customized parts could easily be produced without going through the hassles of number of manufacturing techniques to produce a customized part with complex shape. One can also produce one-of-a-kind product, one-of-a-kind part. And once we have the digital inventory, we can scale down, we can scale up, we can produce part variations within the same design parameters or limitations. Very less time is required. Once we have the design with us, we create the drawing, then very limited time is required, very small time is required to create a 3D printed part using additive manufacturing, which is nothing but layer by layer deposition. And then no specific tooling is required. So we save on the tooling costs. Fixturing cost is also reduced because we provide the support material to hold the workpiece. We have to provide for a suitable technique of orientation so that the part could be laid on the surface and then easily removed from the surface. For that, proper orientation is required to deposit the layer in 2D and then build layer by layer and go in the third dimension to achieve the desired shape and size. So the obvious benefit is that the speed of development of product life cycle in the product life cycle is enhanced. It reduces time in cost and cost in manufacturing because one does not have to go through a couple of processes before the part could be made. If we produce the first component and if there are flaws, we can rectify the design. Whereas in the conventional manufacturing process or even in the non-conventional process, we may produce a part to realize, to understand that there is some defect which merits reconsideration of design and reproducing the component again. It takes a lot of time. Here, one can easily prepare the next prototype by making small changes in the design or correcting the design. So complex parts where extensive tooling could also be avoided, one can look at additive manufacturing as a technique or as a method to produce parts. So this was well conceived by Professor Beeman and Carl Descartes. And then in 1986, I'm sorry, 1984, Mr. Descartes produced the first 3D printer using stereolithography technique, and he patented this in 1986. Normally, patents have a life of 20 years. After 20 years, they become open source. One can easily duplicate or replicate. So that is why until 2006, this technology was very, very expensive because it was patented. And once the patent period was over, each one made an attempt to create machines what were invented by Professor Beeman and Descartes in 1984. In 1992, first 3D printer was built by 3D Systems. And in 1999, the human bladder was printed. 2000, human kidney was attempted. 2006, selective laser sintering machine was conceived. In 2009, prosthetic leg, artificial limb was customized for a patient. And in 2011, people started using 3D printers for making ornaments. When we talk of prototypes, we say 3D printing technique. It is customized. It helps us to prototype. We are all familiar with virtual prototypes, paper prototypes, form prototypes. But what really matters today is the alpha prototype. You conceive a component, maybe using alternative materials. You print components and the sub-assemblies to see how the final shape and size will look like, how the sub-assembly will work. We may also integrate that sub-assembly into the assembly to see how is the performance. So that is the alpha prototype. And then we come to the beta prototype, which is a full functional model. A full functional model of the materials that we actually want to use in practice of creating a prototype which could be tested in its true sense. And then if there are any changes or modifications required, those changes could be done to come up with a production prototype. So we go through different phases of prototyping from alpha to beta to production type. But once we achieve the production type prototype, which means that it is able to deliver the desired function with a given or with a calculated reliability based on the quality that is built into the product, then we start producing that product in numbers. And then we attempt at mass production. But 3D printing is still a slower technology. But yes, we don't have to use the primary processes of creating raw material, of sheets, of rolled steels, of ingots, of different forms, extruded forms, channels. We don't have to create those and then use the machining process to remove some of the material to create the product. Here we can use the raw material directly. Of course, it has to be in some form to be used on the 3D printing technique. So basically, we create a 3D model. From the 3D model, we create a file, a tessellated file, structured tessellated file. It's called the file with an extension .stl. It's a file of triangles. Triangles using a slicing software. We are able to build the tool path of each of the layers. These triangles help us to ensure C0, C1, C2 continuity between different or adjoining surfaces. Slice the triangle into different layers of varying thicknesses and build or print layer by layer and build the model. So from 3D CAD model, we are able to build the 3D object, So we can create a 3D model of required shape and size, provide tolerances to that, print it, and then if you want, we can check the object with for required shape and size and compare it with the intended shape and size that was there on the sketch or in the CAD model, and to see what is the accuracy level that we have obtained, find out what is the finish that we have obtained, and whether it can be accepted to be a part of the entire product or the sub-assembly. There are different methods of making 3D printed parts: the selective laser sintering technique, stereolithography, fused deposition modeling, laminated object manufacturing. I will quickly make a mention of each of these techniques, as you would get to know more of these techniques when the experts make a mention of achieving a certain class of product using one of these techniques. So the stereolithography technique makes sure that one can build plastic parts. So it is converting that plastic part, that liquid, into a plastic part by tracing a laser beam on the surface of the liquid. The liquid surface, which gets treated by the laser, solidifies into the required part size, part shape. And then this can go on layer by layer for building the part. There is a fused deposition modeling technique where we have extruded wires, most common plastic wire is the ABS wire. We can use PLA, we can use PEEK, different types of plastics to build the object layer by layer. This is fused. So the wire, plastic wire, is fused at the given temperature, and then it is deposited layer by layer and allowed to solidify before the next layer can be placed. We have selective laser technique, wherein the powder is rolled into the required cavity and then hardened by the laser, cured by the laser, and then what you get to see on the sketch is a layer by layer deposition. So the piston brings up the required quantity of layer. The cylinder moves over, spreads that layer into the desired cavity, and then that is curated by the laser. And then we have laminated object manufacturing, which again uses lasers. We have paper roll, and the desired paper is cut by the laser and deposited again layer by layer. The layers of paper are glued to give the desired height of the object, but this also goes layer by layer. So if you look at additive manufacturing today, it is used in defense and space, in fashion, in retail, for medical applications, food products, food industry, for games, entertainment. Each of these domains derives its purpose from additive manufacturing. I happened to get this chart from one of the magazines which carried this survey on how 3D printing is used in a variety of applications. And if we see the functional models, the artistic items, the spare parts, the research purpose, find greater deal of applications compared to presentation parts or visual aids or patterns or more, but can be used in a variety of ways, number of ways. In dental applications, used in artificial limbs, cylinder design. So if you see the lowermost portion, that is the support material which needs to be removed prior to using the actual component that is meant for use. The body parts of the car. So it would be in 2011. They made the first car which was made of parts which are all 3D printed. So including office spaces, the office buildings. Today in the construction industry also, concrete is laid using 3D printing techniques to build the buildings at a faster pace, to come out with the required curvatures and shapes that we require inside the building without having to use any manpower. So the construction industry is also moving towards 3D printing. This is again using 3D printers in the food industry. In the apparel industry, making shoes, garments, wearables. In the aerospace industries, coming up with complex structures. We have a 3D Make Lab at COEP, which talks of the 3Ds: to discover, to design and develop, from concept to creation. So these are some of the facilities that we have in the lab today. We have FDM printers based on rapid fab techniques, printers which are using ABS plastic, printers which are using different kinds of resins, metal printer using the SLA technique. We have also printers using printing resins which are used in biomedical applications. Printers printing hydroxyapatite structures which can go into the bone tissue. All of these printers are there in the lab today at COEP. We have very good scanners. So if we have a used part or a worn part, we can scan that go to the CAD model, correct its dimensions, and then put it to printing, and that the spare part could be then provided to the end user to be used onto the machine. So good variety of 3D scanning facility is also available in the department, in the lab. We run a 1-year full-time course on additive manufacturing. It's a trimester pattern course where first 16 weeks there is coursework and lab work. Next 16 weeks, it's a full-time course. There is coursework and lab work and mini project. And the last 16 to 20 weeks. So first 16 weeks, then the next 16, 32 weeks, and the next 16, 48 weeks. 48 to 52 weeks, that's 1 year. It's a full-time course. Last 16 weeks to 20 weeks, that is 4 to 5 months. Students spend in the time in the industry doing internship and working on real life projects in the domain of 3D printing. And they, after 1 year, they are conferred with a postgraduate diploma in additive manufacturing. So this is one of the activities that is taking place in the department. We conduct many workshops on 3D printing, how to make 3D printers. You can create your own 3D printer in the lab and use it in the lab for making different components in plastics and polymers. So using open source code that is available, using open source code for programming, or using G codes for deposition of the material layer by layer. Different slicing softwares which are available in the open source format. We make use of those, a combination of those. So we don't make use of any proprietary software or a product, use all open source way. And mechanically make our own machine and use these open source codes for printing material. And using this technology, we are able to print machines. So machines, replicating machines. We are able to print our own 3D printers, except for certain bought out items, like motors and heaters. Even the nozzle that we use, we can print ourselves. The pulleys, the cords, each of this is printed and then replicated to make another machine. So there are certain bought out parts, the PCB electronic circuitry, which we also make in the lab, or it could be bought out. Make the mechanical structure. Most of the parts in the mechanical structure are made on the 3D printer. And then it's like machines making machines. And the entire software is through the open source code. Here what you get to see is a development of a metal printer in the lab using the SLS technique. And we have been able to print parts made of brass using a fiber laser, a 400-watt fiber laser, to make brass bushes. So we are not using a 3D metal printer, but we have created our own metal printer to produce parts using different combination of materials. And that is why we said it's worthwhile visiting some of the labs to get a feeling and hands-on exposure to what is being done in the lab. This is a different version of the metal printer that we are making. If you look at this, it is comparable to any finished 3D metal printer. The entire mechanism, the entire assembly costs less than rupees 2 lakhs. However, the cost of laser is very high. We spent 30 lakhs in getting the laser and 2 lakhs for developing the machine. Now this is a small 3D metal printer. A printer of this size in the open, which is a proprietary product, would cost anywhere between 2 to 3 crores. We have been able to make one at a cost of 2 lakhs plus 30 lakhs cost of the laser. So 32 lakhs is the cost of this machine as compared to 2.5 crores in the market. But it's the cost of the laser that becomes the inhibiting price. Otherwise, to make machines, it's very, very economical. But you must come to the lab to see the facilities, experience that you too can create such small 3D printers for application in your own lab. This is a glimpse of different parts, different components that we make for the industries in and around. We also have a wax printer for investment castings. Here what you get to see is a lady who lost one earlobe, and then the doctor came to us from AFMC, Armed Force Medical College in Pune, a prosthodontist. He came to us with a picture of the right lobe, and using that picture, we were able to create a mold for the left ear, and then he poured silicone into that mold and then created an artificial ear and sutured that artificial ear made of silicone. He matched the tone of the skin color with that of that ear, and he sutured that silicone ear onto the girl's face, and now she has both the ears. One cannot make out the difference from a distance. They look as though they are both real ears. So this is some of the work that has been done in the lab. We have done a lot of work for spine surgeons, for dentists who make use of these techniques, because for the spine surgeons, for the dentists, this is patient specific. Whatever solution we give is for a given patient. As the patient changes, the patient's anatomy changes, the solution to be provided to the patient also changes. So it becomes patient specific. But we have been able to deliver a lot in the biomedical domain. We have a lab, an incubation center in the domain of biomedical devices, implants, a center which is established in association with leadership from IIT Bombay, COEP and VNIT Nagpur, Biomedical Engineering and Technology Incubation Center, BETIC as it is called, conceived and originated at IIT Bombay by Professor Ravi, the principal investigator, and then we have a center at COEP and one center at Nagpur, VNIT Nagpur. And we have been doing a lot of work in the domain of providing low-cost solutions to biomedical devices and implants. In addition to developing, creating engineering products and services for the industry in and around Pune. So the seahorse tail concept is also used, which is normally used in aircrafts. Similar concept was conceived by students to create one small prototype for their project. So we are doing a lot of work, design modifications, design for additive manufacturing, using additive manufacturing for non-conventional machining, working on the nozzle optimization, developing biocompatible materials. We have also developed our own vapor polishing machine. So after the products are made, they are kept in the vapor polishing machine for a certain duration of time. And the vapors help polish the surfaces, refine the surfaces, make the tough surfaces into smooth surfaces. It's our own technique that has been patented and developed in the laboratory in the department. So a lot of work is going on, and the advantages that we see from this technology is that any complex component can easily be 3D printed. You can print a variety, one of its kind. If there are a couple of sub-assemblies, we can integrate them into producing one integrated sub-assembly. Very little lead time is required to create a prototype. Not much skill in manufacturing, because once the CAD model is prepared, that is converted into an STL file, which is sliced, corresponding tool paths created for layer by layer deposition. So there is not much skill required in actually cutting the material or removing the material or forging or drawing the material. This is layer by layer deposition. Fewer constraints. One constraint, as I said, it is slow. There is less wastage, zero inventory manufacturing. From one size fits to all sizes to fit. You can customize every component to every application. So there is a great deal of advantage using this technology. So they say people with CAD skills or 3D scanners will make them, and people with printers will buy them. So this gives us another opportunity in the developing world. Some countries are developed, some developing, some underdeveloped. But this technique is there to stay for each of these worlds, to help convert the CAD file into a component or a part or a product. And then make use of them for a variety of applications. So what matters today is addition of creating components layer by layer. With this, I conclude my talk. If there are questions, I will be happy to take those questions. And if there is someone in the audience who has an answer to those questions, I will be happy to listen to the answers from the audience rather than taking answers from me. And more of this technique you would learn as you go along, more applications, more focused discussions will happen. This is only creating awareness of the potential of this technique, but I'm sure the entire week will tell you much more of each of these dimensions of this new emerging technology. Thank you. Thank you once again.
Good morning once again, all of you. Now, one by one can ask the questions by unmuting themselves.
Can I ask one question, sir?
Yes, please.
Yeah, sir, actually you have indicated that that low cost 3D printing machine has been developed. Has any company has taken up for productionizing it so that we can buy it? Or is it a metal printer or it is other things?
We have developed both. We have developed a plastic printer in 2015. And since then, we have been giving this technology to the colleges, to the institutes. 3D metal printer is currently only in-house for doing research. But once we are now working on, using a combination of different metal powders in combination to print variety of metal parts. Now, once we achieve that, then we can probably take it to the industry or keep it open for sale. But that is maybe 6 months to 1 year down the line. But 3D plastic printers are already established. They are working well, and we have been using them for the last 6 years. But they are made in the department itself. And we are giving this technology to colleges and universities.
And does the department also sell or gift, whatever you say, to any other department or institutes, this
Yes,
metal
yes.
printer? I'm
Yes.
talking of the metal printer.
Metal printer, I said no, not as yet. We are still working on combination of powders. Once we achieve that we can print combination of powders, then we will throw it over.
Okay, thank you, sir.
Sir, there is one question in chat box. They says the 3D printer can be used for poly nanowires.
One moment, let me. Yeah. What is the one minute? Let me read the question in the chat.
This is 3D printing can be used for polymer nanowires.
No, for creating poly nanowires or using poly nanowires, polymer nanowires.
For creating polymer nanowires.
Polymer nanowires, I'm not very sure whether we can use, but I'm not sure whether we can create. Right. So this is something that needs to be discovered. Yes. Yes, in architectural building construction, very much 3D printing can be used. See, basically going in the nano regime, one has to understand that, what is the, depending upon the technique, whether it is SLS or SLA, or, it should be doable depending upon the kind of laser that we are using, and or if it's an FDM technique, what is the nozzle size and the rate of deposition. I think that actually controls the creation of these wires. So um, we have spinning machine which is creating nanofibers, right? But that spinning machine is not using the 3D printing technique. So we are actually printing 3D nanofibers from polymers in the lab, but that is not using 3D printing technique.
Hello.
Yes.
So this is Tyagarajan from Tamil Nadu. In my
Yeah.
previous company, we used 3D printing for developing the steel mold for the particular critical location for a conformal cooling, which can used for the thermal balancing for the heat conduction. So we achieved the effectiveness of the process.
Yes.
And we produce the parts through 3D printing for aluminum casting also. Only thing is the cost of the material. The
Yes.
process is very cheap, but raw material of the additive, the 3D printing material is very high. So, do you have any project or ongoing project for developing the raw material point of view?
Yeah. So currently, uh, I have one of the research scholars working on, using plasma to, create powders from different materials. Uh, and once it is in powder form, then we can use that for in combination to create, as you said, for printing, but we are attempting, so there is one facility available in Pune with the Center for Metallurgy and Electronic Testing, CMET lab, where they use this plasma technique to create fine powders of different materials. So we are attempting to create that machine ourselves first, and then control the parameters, create fine powders of different materials, and use them in combination for 3D printing, metal printing. So somebody has asked a question. Can you please tell me an example of architecture building? Okay. Maybe I don't have the slide now, but if you can, this is somewhere in US where they have used 3D printing for creating architecture, of the entire space. Um, it's a casino, and they have been able to create that architecture and also to build one. So if you can post your email ID, I can send you the pictures of that. I don't have it right now. It's not there in the presentation. Yeah, we welcome any student, any PhD scholar to come and work in our lab. I think the future of 3D printing is more growing towards the construction industry because they are able to use heavy duty printers for creating walls, creating slabs of any shape, any size, and then also because it's layer by layer deposition, so it is constructing one floor after the other and building it up. So the advantage is that the interiors could be designed to the convenience of the architect. They could be built faster uh, depending upon the kind of materials that are used today. The curing time, settling time is also reduced, and a lot of work is being done for the construction industry using 3D printers. But we would want to invite someone who asked us about, you know, about the printing of nanofibers. So we can showcase the facilities that we have for printing polymeric nanofibers using liquid resins, and but of course not through the 3D printing route, but through other technique, other methods. A lot of work can be explored in the domain of biomedical printing. A lot of work can be done in that domain. So one is wanting to pursue a PhD. One can explore using 3D printing in creating biomedical implants and devices. So one of the students is working on, creating a bony structure. So once you have the X-ray and you know how the bone is fractured, then for a given patient, we can create that hydroxyapatite, implant which goes into the body. So there is no need for nailing, and over a period of time, the bone grows into the pores of that implant, and that hydroxyapatite gets dissolved into the bone tissues, and it becomes one joint bone, as though there was no fracture. But it's difficult for the orthopedic surgeons to accept this because, there's a lot of, it's a gray market, because they buy these screws and implants and plates, at, at a price which is just, there's no control on pricing. For example, the stents which go into the while one is doing angiography and angioplasty, you implant a stent in one of the arteries, and then the stent costs maybe $10 or even around that much. But maybe 1,000 rupees, 2,000 rupees would be the cost, but it is sold at 1 lakh of rupees. Now recently, 2-3 years ago, government has brought price control on use, on the stents, price of stents. You can't get it more. The maximum price is 30,000 or something like that. But a stent which costs only 1,000, 2,000 rupees to make is sold in the grey market for 1 lakh. Likewise, these simple screws, titanium screws, which go into the implants along with those plates which to fix bones. Each screw costs 5,000, 6,000 rupees. I mean, it's cheating patients, they have to pay the. So there's a lot of work that could be done.
Sir, this is Tyagarajan from again Chennai.
Yeah.
I would like to know about is it possible to enhance the parts of 3D printed component like improve the mechanical properties or
Yes, yes.
surface
It's very,
engineering of the part?
yes, it is very much possible.
Oh, yes.
It is
Okay.
very much possible. Yes.
Okay. Do you have any case study? Is it possible to share with us?
Yeah, we do have a case study, but I mean, let's see if the organizers give us some time, we can present the. Yeah, case study applied in non-conventional machining. So that is rapidly creating tooling for non-conventional machining with the required set of properties that a tool would have in non-conventional machining. So that is something that we have been able to achieve. Yeah, ceramics, there's a question on ceramics or energy materials. So there is something that is coming up in the lab, but it is in the nascent stage, but yes, they are working on it. Okay, thank you everyone for your patient listening. And please do visit us and see some of the labs. And if time permits, if there is some more slot, probably we can discuss more case studies of the work that is actually happening in the lab, right? Which is one is making machines, the other is using machines for a variety of applications.
Okay.
So thank you, Appa sir. Thank you,
Yes,
Professor
sir.
Butti. Yeah, thank you.
Thank you once again for your very informative session and providing a good insight on the future trend in the 3D printing and what are the research and development areas to work for all the faculties and participants. Thank you once again, sir, for enlightening us. Thank you.
But you are all welcome to COEP, and please come and visit these labs. If you want to work in the labs also, you are welcome.
Yes, sir. Thank you, Ahuja sir. Yeah, it was a indeed wonderful talk. You all gave very wonderful insight into what manufacturing is, then how industry 1 to industry 4 we are moving, how disruptive the technology is, how now AM would be okay useful for the world. And I understand, like in online mode, okay, it is really okay since the classroom teaching is not there, but definitely like your lecture was very impactful. We have really liked it. Thank you very much for your okay for setting the ball rolling. Yeah, and I understand in spite of your very busy schedule and all, you could find time for academy or teaching and all. So that is indeed a lesson to learn from you, sir. Thank you very much.
Yeah. Thank you. Thank you for giving us opportunity. But
Yes, sir.
you can ask Dr. Mrs. Aarti or someone in the lab, to give them 1 or 2 sessions. Sheikh is there. His work can be presented.
Yes. Yeah, that we will
His work,
include. Yeah.
yeah, Sandesh's work. There are lot many things that we are actually working on. The case studies could be presented as to, with what.
Yes, definitely. Yeah, definitely we will. Okay, we'll ask Sheikh. Yeah, Aarti madam, she would be okay giving a talk, but
Yes.
Sheikh also we will do some okay case studies, some live demonstration. That we will definitely, sir. Yeah, thank you for your this valued suggestion.
Yeah. Thank you.
Yes, sir. Yeah,
Thank you,
thank
sir,
you.
once again.
Yeah, so Appa, any announcement you want to make some?
Yes, next session will start on 11:50 after within 6 minutes.
Right. So give just okay
Small break.
break, 5 minutes break you are giving, huh, Appa?
Yes, sir. Yes, sir.